Hello and welcome to this Xilinx quick take video which will briefly introduce you to the conversion of UCF constraints to XDC. This is a big topic and we'll not be able to cover all the necessary details in a short period of time. This video will give you a quick introduction to the XDC equivalent of UCF and how to convert some basic constraint concepts. The agenda for this presentation is the following. We'll give a little background on UCF tool support and how to begin to migrate to the equivalent XDC. We'll cover some basics of timing constraints, then physical constraints. Then we'll discuss a conversion utility that exists in PlanAhead to help you get started. Finally, I'll show you a brief demo of the conversion process on a simple example design, and we'll wrap things up with some pointers for more detailed information. Most ISC users will be familiar with the UCF constraint file format. Unfortunately, UCF is not supported in Vivado. The reason for this has mostly to do with timing constraints, and the significant difference is how the two are interpreted by the timing engine. A detailed analysis between these two is not the topic of this presentation, but suffice it to say that there is no guaranteed way for a tool to convert the designer's intent between these two constraint systems, so the designer must do it themselves. If the designer is familiar with SDC, a manual conversion is probably not difficult, but a large portion of our users have been using UCF for a long time, and this is not a trivial task. Fortunately, we do have some helpers to give the users some guidance. PlanAhead does support UCF because it works with the ISC tools, so we have developed a translation utility that can do some of the work of this conversion for you. Physical constraints are the easiest and they convert with relative ease. Timing constraints are trickier. Basic constraints can be converted, but there are many ways of constraining things with UCF that have no direct equivalent in XDC, and the designer will need to manually review every constraint. In some cases, new constraints are needed, and the user will have to consider how to achieve the desired result with SDC. Here is a basic table of timing constraints and the mapping between UCF and XDC constructs. The most important constraints are always clock specifications, which in UCF are achieved predominantly with period constraints and time specs. In XDC, clock constraints are specified with the create clock constraint. I/O timing constraints are specified in UCF with offset in and offset out constraints. In XDC, the equivalent are set input delay and set output delay respectively to tell the tool what are the data arrival and required times external to the FPGA device. There are also many exception constraints which override or change the analysis on specific paths. The most important is the timing ignore constraint, or TIG, in UCF. In XDC, this is achieved with the set false path constraint. Now it gets a little more complicated. Many constraints in UCF that can be described with from, through, to, and T&M constraints have no direct equivalent in XDC. The closest equivalent to a from, to constraint, where you apply either a clock multiplier or a fixed delay that is a multiple of a clock period, would be the set multicycle path constraint. Other examples of fixed delay constraints would be max delays. Again, the closest would be the set max delay constraint in XDC, but the expectations are not exactly equivalent. Since XDC is based on SDC, which is an industry standard constraint behavior, we are aligning with that industry expectation about these timing constraints. There will be more specific information on these individual constraints. This is merely a high-level mapping to give you a starting point of reference. Physical constraints include everything that is not part of static timing analysis, and most of these constraints are very similar in Vivado to what they were in ISC. If you look at a UCF file, most physical constraints are attributes on netlist objects, instances, nets, ports, etc. It is very similar in XDC. We've mapped all of these attributes to an XDC equivalent, while keeping as many of the original attribute names as possible, since these will have likely been written into RTL by many users, and they would not want to alter or rewrite their HDL. Some examples would include location constraints for placement, IOB, and IO standard constraints. Here I show the equivalent of UCF location constraint in XDC, which is the lock property set on a cell object. There are physical constraints that change names, mostly because the behavior is slightly different. Area group constraints are referred to as P-block or physical block, which was a long-standing PlanAhead floor planning feature. Package pin constraints are the XDC equivalent of a lock on a device pin. Mark debug constraints was added for chip scope probing to preserve nets for the analyzer. Don't touch constraints preserve nets, pins, and cells and prevent optimization. There are others. These are some of the more commonly used ones. In order to use the conversion utility, you need to invoke PlanAhead on your project. You can do this in several ways. Launch PlanAhead from the integration with Project Navigator via the process tree. You can also open PlanAhead and use the new project wizard to import and convert an ISE project file. Finally, you can create a new project with Edith and UCF, but you need a project with a post-synthesis netlist and a matching UCF to perform this conversion. Once you've done that, open the design in PlanAhead, and it reads in the netlist and applies the UCF constraints to that netlist. Now you can use a tickle command to export out an equivalent constraint file in XDC format. This is not just a simple text translation. PlanAhead has parsed and applied the UCF constraint so it has the best chance of converting to the correct equivalent constraint file. When you run this tickle command, you specify a file name and a location to export to. It is important to review and understand any warning messages that are issued either to the console or in the produced XDC file. Now you can take this XDC file and use Vivado to create a new project. We recommend you only use this XDC file as a reference to give you an idea of the equivalent constraints in XDC. The designer is the only person who can qualify the constraints provided to the tool, particularly the timing constraints. This is why we do not attempt to automatically convert UCF to XDC or support UCF directly in Vivado. Now we'll jump to a quick demo of PlanAhead and show you how to use the translation utility to convert XDC from UCF. Here we have a simple example design with UCF constraints. First, I will open the synthesized design to read in the netlist and UCF constraints. I can click on the Sources tab and expand the sources to see the constraint files in my project. If I click on bft-full.ucf, which is the active constraint file, I will see my UCF file. This is the file we wish to convert. Note the period constraints and the I/O constraints. Now I can type in the tickle console a command called write_xdc, which takes a file name as an argument. I can place the exported XDC anywhere I want with any file name I want. When I hit enter, the tickle command is executed. Note the warnings and messages produced in the tickle console. Most of these are due to a translation of a net UCF constraint to a port object. The warning is telling you that it's moving a constraint from a net to the port connected to that net, which might be a problem if the design netlist you intend to apply the XDC to has net names which are different than the top-level port they are connected to in your RTL. This is not commonly a problem. The point is that some of these constraints do not translate, and you need to review the produced file and the error messages. Now we'll open up the file we just produced with a text editor. Note a couple of things. The header gives you the version of the tool which converted the constraints and some disclaimers. The first constraint that was converted was our period constraint, and the tool gives you the line number 2, from the original constraint file right above the translation. Then you will see all the I/O package pin constraints locking down the ports. Then you will see that we translated all the I/O standard constraints from their net objects in the UCF to the port connected to the net, and the line from the UCF file where the original constraint came from. As long as the port names match up, this will be okay when you apply the XDC in your Vivado project. The tool is being verbose in reporting its translations. We just saw a very brief demo of some tools to help you convert UCF files to XDC format for use in Vivado. We realize there's a lot more details needed to convert complex constraints, but this should serve as an introduction to some of the tools available to assist in this conversion. Please consult the Vivado landing page on Xilinx.com for links to documentation and tutorials that will help you get familiar with this process. In addition, there will be more quick-take videos available on specific topics to help you get started. Thank you for watching.